Hello and welcome to YMT215 Logic Circuits. We are still discussing Chapter 2. This is Part 2, Number Systems, Operations and Codes. In this part we will cover sign numbers, arithmetic operations with sign numbers. These two topics are a bit long, so that's why we assigned one part for them individually. Okay, signed numbers. Now, why do we need even to discuss signed numbers in computer? The computer understands only ones and zeros, so how can we represent a negative number? So in order for us to represent a negative number, we need to find a way to represent the sign. And in that case, it should be by a bit, means by a representation of 1 or 0. So in this case, what we do is we assign a bit for the sign, and we indicate the sign based on the existence of 1 in that bit. If there is no 1, if it is 0, then the number is positive. If it is 1 or otherwise, it would be negative. And that is how the computer represents signed numbers, or actually numbers with sign in the consideration. What we refer to here is something we call uncomplemented form. We spoke about the ones complement and the twos complement, and we will speak about the relationship between these two within the coming slides or during this session actually. Now look at, this is a simple example in decimal 25. If you want to represent it in binary, it's easy actually. You can use the weight methods, 16 plus 8 plus 1, right? So in that case we have 16 plus 8 plus 1. How do I know? Let's just revise it quickly. 1 is 2 to 0. This is 2 to 1, there is no. 2 to 2, there is no. 2 to 3, which is 8, so we have 1. 2 to 4, which is 16. So 16 plus 8 plus 1. So here we don't have, here we don't have. Okay, this is what we call 8-bit sign number or 8-bit system. Why do we choose 8-bit? It could be more than that, just for simplicity. It could be even less, 4-bit system. But 8 is average, usually average for representation. I mean, it's convenient for us to represent. Let me get the pen. Okay, the pen. All right. So here what we are looking for is a designated bit, this one. Not that one, I'm sorry. This one, yes. The leftmost or the most significant bit in this case is reserved for the sign, okay? And in this case, the existence of 0 means that this is positive. If it is 1, then we are referring to a negative. How? Look at this. This is 1. So this is true uncomplemented, and I'll explain about the complemented and uncomplemented soon. But remember that this is uncomplemented. It's a true form. It's not changed. It has no twos complement or no ones complement. It is just the true form of positive and negative. We reserve the bit for the sign. So the same value of 25, exactly the same. We just place the sign bit by 1, or actually we change it or we set it to 1. That's how we represent the sign in this case. Okay. We have another way to represent the sign number, and they said that is the true version, this one, uncomplemented. We have the complemented version. We can use the ones complement to represent sign numbers. How? Take the ones complement, and that is the case where we will have a complemented value for a signed number. What does it mean? In this case, if you think about converting a number, a positive number, to a negative number, take the ones complement, okay, and we have a final part. We need to just change. Now look, for 25, let me just explain here. I don't want to go deeper before giving an example. For 25, we said 16 plus 8 plus 1. So this is 16, the weight for 16, plus 8, the weight for 8, and then we have the weight for 4, the weight for 2, 0, 0. Then we have the weight for 2 to 0, that means 1. Okay? So in this case, what we are having here is true uncomplemented. If we take the 1's complement, we can get what we call minus 25 represented in 1's complement. So this one is complemented form. Okay? If you want to do the same using 2's complement, do you remember the essence of 2's complement? We explained about it in the previous video. It's actually generated from 1's complement in two different ways. Either we take the 1's complement and we add 1 to the final result, or we check the number, we hold the number the way it is, we move until we catch the first 1 from right to left. Once we catch that number or that 1, then we take the 1's complement of the next part of the number. How? Let's just look at it again. This is the 25 positive true uncomplemented here. 16 plus 8 plus 1. So this is true uncomplemented. If you want to take the 1's complement for it and then get 2's complement from 1 complement is possible. How do we get 1's complement? Invert each 1 to 0 and each 0 to 1, then add 1 to the outcome. Alright, we have an easier method. We pass through the number from here, from right to left, and we catch the first one that comes with us. This is the first one. Catch it. Whatever. It may be here. It doesn't matter. So whatever you catch, separate the number to two parts. This one inclusively, the one with it, and then this is another part. So keep this one the way it is, and the part with it. It may not be the first. It may be second, maybe wherever it is. Hold it, then take the 1's complement for the rest. Okay, so we take the 1's complement for the rest, we invert the 0 to 1, the 0 to 1, so 1, 1. This one remains the same. Then 1's would be zeros, so these two 1's will be zeros, and then these three 1's will be, 3 zeros will be 1's. And this is the 2's complement form for 25, and it is negative. How do we know? We have actually the sign bit in this case, but it is true. It is not true. Actually, it's complemented form. 2's complement in this case. Okay. Now, if we want to get the values back again from signed numbers, how can we get them? As I said, in computer, we don't exactly understand a sign minus. No, we need to have a replacement for that sign. And as I said, we have a sign bit for that. How about the weight? How about if we would like to get the real value of a number represented in a sign form? How can we get it? It's not really hard. We can use the weights. Now think about this. Let's just take an example, straightforward, where we have a direct application of such a scenario. Now look, this is a number. How do I know if it is signed or not? Usually we mention that it is signed. The question, look, signed binary number. And it is expressed in sign magnitude. Okay, sign magnitude means this one is reserved. Reserved for what? For the sign. The rest belong to the number, yet this one is reserved for the sign. So it doesn't exactly belong to the number, it belongs to the sign. Now if you want to get the value of this number, you start from here. So 0, you don't have to bother about it. Also 0, you don't have to bother. Why? Its weight is multiplied by 0. So, well, anything multiplied by 0 is 0. How about this? So if you want, you can start from here or here, it doesn't matter. 2 to 6, this one ignore. 2 to 4, this one ignore it also. 2 to 0. So what we have here, 2 to 6, sorry, I got a bit confused. This is 2 to 6, 2 to 5, 2 to 4, 2 to 3. There is no 2 to 2. Oh, I think I made a mistake. Did I? I missed one in the yes. I missed one in the calculation. Okay, 2 to 6, which is actually 0. It has no weight multiplied by 0. 2 to 5, also multiplied by 0. 2 to 4, so this one is included here. Okay. 2 to 3, also 0. 2 to 2, this one is here. Okay. And then 2 to 1, one of them I missed while I was counting. also dropped 2 to 0. So what we have here is these weights, these three, this one, 2 to 4, 2 to 2, 2 to 1. So 2 to 4, 16 plus 4 plus 1, that's 21. But remember that we have the sign bit, so this is negative. Okay, so add the sign bit, add the sign to the number, and that represents the whole number in decimal. So again, we find the values based on the weights, okay, and then we assign the sign based on the sign bit. Let's take another example. I think we have. But never mind, there are many examples coming. Assume that we have another form that comes with us, not just true and complemented. This is true and complemented. That means it has no one's complement, neither one is complement, nor two is complement. So it is just in the true form. Okay, the true form is uncomplemented in logic circuits terminology. In that case, if we have a complemented form, so we have two types of complemented form, one's complement and two's complement. So for one is complement, how can we get the value in decimal, for example? We need to add the values and we need to add 1 to the final answer. What does it mean? We need to sum them up, but there is one exception. The last digit, or the most significant digit, will be considered negative. So this one will be considered there with its weight, but it will be considered negative. So this negative value will be subtracted, actually not added. So eventually we will subtract this one from the rest of the weights. Of course, this is the highest, so it is higher than all of them. And in that case, we will get a negative value, but do not forget to add 1 to the outcome. How do we do it? You are a bit confused now? No problem. Take an example. Determine the decimal values of the signed binary numbers expressed in 1's complement. So we always say that expressed in what? If they are true and complemented, complemented in 1's complement. So if they are 1's complement or 2's complement, we have to mention about all these. Okay. So here it's mentioned 1's complement. All right. So initially, if we look at this one, what we need to do, we need to place the number based on its own weights. What does it mean? Weights, now, if you count 3 plus 3 plus 2, this is 8-bit system, I said earlier. We use it a lot and it has a lot of applications. It will come after a while. Why? Look at this. This has the weight of minus 2 to power 7. How do we know 7? Go through the weights. Minus 2 to power 7. But this is minus because it's the sign bit and it is in 1's complement. The rest, 2 to power 6, 2 to power 5, 4, 3, 2, 1, 0. Okay? So sum up the magnitudes here, or the weights. These zeros you have to ignore them. Also the sign is ignored. 0 times anything is 0, so you don't have to do that. Also here you don't have to, but 1 times 2 to 4, so we directly say 2 to 4 plus 2 to 2 plus 2 to 1, okay, plus 2 to 0. And that is exactly how we get the calculation or the outcome. It is in 1's complement, but it is positive. It's possible. You may have in 1's complement positive values and negative value. It's possible. Okay. Let's take the second example. The second example, you see the sign bit is there. So it is likely to be a negative, and directly we can apply the rule. So we have 2 to minus 7, and it is minus. Okay. Minus 2 to power 7 is minus 128. Okay. So here we have 2 to 6, that is 64. 2 to 5, that's 32. This is 0. Then 2 to 3, that's 8, and the rest are zeros. So minus 128, minus 48, that's half of it, so minus 48. Minus 32, that's half of it, so minus 32. Plus 8, that's 24. Now wait, we haven't yet done. Remember that we need to add 1. So minus 24 plus 1, that is the final result. And that's how we calculate it. Remember, start from the leftmost bit, sign bit for the ones complement. Calculate the magnitude. If it is negative, if it is available, I mean the 1 is set, or here there is 1, multiply it by minus 2 to 7, then add the rest of the weights, and this one will be negative. You subtract it from the rest of these weights. All right. For 2's complement is also straightforward. All we need to do is we apply the same concept here. We just do not add this one. There is no adding 1. You apply the same concept, exactly, literally same. You sum up and subtract this one if it is available. And you apply the rest of the steps, except adding 1. There is no 1 added to be added. Now, in this case, this is positive. We see this one is not set. This is negative. You see this one is set. And it is written, determine the decimal values of the signed binary numbers expressed in 2's complement. So it is mentioned that they are expressed in 2's complement. All right, so good. Let's take one of them. Let's not take this. This one is easy. Let's take this one directly. So look at the weights. Now for the sign bit, we have 1 set. So its weight is minus 2 to 7, minus 128. Summed up with what? This one is 0. So 32. This one is 0. 8. This one is 0. 2. So minus 128 plus 32 plus, this one also 0, plus 8 plus 2. That's minus 86. There is no 1 to be added. That's it. I usually ask these questions in quizzes and exams, so pay attention to that. Now let's go to another topic. We have what we call range for signed integer number. How do we represent numbers? We have integer numbers and floating point numbers. Integer numbers, numbers with no decimal point or with no point, because we speak about decimals and also we speak about binary. So we don't have mantissa. Mantissa means whatever next to the point. If it is a decimal point or a binary point, it doesn't matter. Now, if we think about 8-bit group, we refer to 8-bit group by byte, and you guys are familiar with this, why you studied it, and also in Java and Introduction to Computer Science. Okay, 2 to 8 gets us what? 8 bits, how many combinations do we have in this case? 2 to 8. That takes us to 256 different numbers. So we can represent 256 different numbers, and usually this is little. If we take 2 bytes, so to 8 bits, that means 16 bits, 2 bytes. 2 to 16, that's 65,536. So 65,536 different numbers or combinations. If you take 4 bits, it will be extremely high, for more than 4 billions. More than 4 billions combinations. And that's how we represent usually. There are like ways for representation, yet it's not exactly straightforward like this, especially for floating point number, and we will see how we represent it. This is the formula. We raise the number of bits to 2, so 2 to power n, and in that case n is the number of bits available for representation. How many bits you will represent your number with. Is it 1 byte? That means 8 bits, 16 bits, maybe 32 or whatever. Okay. How about the range? The range is easy because we have negatives and positives. For that case, what we have minus 2 to power n minus 1, 2 plus 2 to n minus 1. So this is in the power, minus 1. Why do we have this minus 1? Because we have a number, 0, is always attached to positives. Now, I will not go to the debate whether 0 is positive or negative. I'm not going to that direction. But what I'm saying is, it is included along with the positives, okay? So if you think about 4-bit system, 2 to 4 minus 1, that's 2 to 3. So minus 8. So minus 2 to 3, that means minus 8, 2. 2 to power 4 minus 1, that's 2 to power 3, 8 minus 1. So from minus 8 to 7. If you count those, these are 16 numbers, including the 0 in between. So from minus 8 inclusive to plus 7. okay, inclusively. All right. Floating point. So that was the integer. Integer is straightforward, but for floating point, usually we get stuck with the mantis, especially mantis if the mantis is too big, the fractional part. So whatever after the point, if it is decimal or binary point, usually we have a problem with representing those. And that is why we have different formulas for representing floating point numbers while saving memory. This is extremely critical and important. Why? Because we don't need to get stuck with, I don't have enough memory to represent these digits, okay? Now the idea is like this. For any floating point number, what we refer to floating point number is real number with a decimal point or a binary point if you speak about digital system. In that case, what we have actually the integer part of the number. Integer part is left to the point, and we have the mantissa right to the point, which is the fractional part. And what we can do is we can convert the whole number to a mantissa. What does it mean? If I have a number like this, I'll take this number. Well, I can pull these two numbers inside the mantissa. That means after the decimal point, because this is decimal. How will I do that? If I multiply it by 100. So if I say here, the same number, but 0.23, okay, the rest of the number multiplied by 100. And in that case, we will get the same number, okay, but after the decimal point. So we transfer all of it to mantissa. This is possible. So in this case, what we refer to is we are taking something we call exponential form. You studied this in Java. We call this exponent. Well, we can manipulate a number with exponent easily. Why? Because the exponent here, I don't have to say multiplied by 100. I can say multiplied by 10 to 2, 10 to power 2. Well, I have exponent here, and I know the base. Okay, that's good enough. What's the relationship? That shortens the representation. If I place a mantissa by certain precision, we'll speak about precision in a while, and then I provide a value for exponent. Exponent can grow too much high depending on the values that you are representing. Exponent, let's say 10 to 2, that's 100. 10 to 10, that's a very big number in this case. Okay, so we can manipulate it. The digits here matter a lot. Okay, so think about it. What we are doing is we are transferring the whole number to a mantissa, and we multiply by certain base fitting the number. Here is decimal, so we multiply by 10. If it is binary, we multiply by 2, depending on the base of the system. And then we change the whole system to what? To exponential form. So these are 2, 4, 6, 7. If I multiply by 9, I can add 2 zeros here and change the whole number from its natural form to a mantissa, okay, fractional form. All right. We have different precisions. I said we have single precision. You studied this also, I think, in Java, if I'm not mistaken. 32 bits. We have double precision, 64 bits. And we have extended precision, 80 bits. That's too high. So we have 80 bits for representation. Let's just think about the small one, 32. That's manageable. We can manage it. And this is a standard, by the way. This standard, you can, if you are interested, you can check this one as a standard. ANSI IEEE standard for 754, which was produced in 1985. This is a standard you can check. These are actually precisions based on this standard. Okay. Let's take the simplest, the single precision. I'm not going to teach you the rest. They will consume our time. This is enough. And even if there is any question, I will ask it from this only. So how the single precision is represented in floating point? Now look, I said we have always a sign bit reserved. And then we have number of bits for the exponent. 8 bits. 8 bits earlier we said 2 to 8 can take you up to 256 combinations. Okay, keep it in mind. So we have 8 bits for the exponent, and then we have the mantissa, the fraction, and we said we convert all our number to a fraction. Okay, this is decimal, don't worry, this is digital. I will teach you how. So we have the sign bit. It represents the real sign of the number, if it is positive or negative. If it is 1, it is negative. If it is 0, it is positive. All right. So we have the exponent, and the exponent is biased. Biased means what? In order for us to compensate for big numbers, we add 127 to the exponent. We make the exponent big, in other words. Making the exponent big means we take really high precision in this case, a lot of numbers included in the mantissa, okay? And we have 23 bits for the mantissa. This is the division. So altogether 32, 1 bit for the sign, 8 for the exponent, and 23 for the mantissa. Sum them up, that's 32. That's single precision. How do we represent it? Now I said, for the sign it is 0 or 1, it depends on the sign. For the exponent it is biased. So biased, we add 127 to it. Now do not ask me why 127, it has a reason, you can look it up. But the standard says 127 for a reason. So we will stick to this one, but please check why. Take it as just, whatever task. Just make a research about it, exactly why. Not, let's say, 255, for example. Why 127? Why not, for example, 63? Think about it and just look this one up on the internet. And then we have the 23 bits. Now remember, this is, I didn't say actually, now I'm saying it. If you look at this, we have here 23 bits, but what we do to save actually time and effort, we take the most significant bit of this 24 bits here, we take the last one, the most significant, we keep it 1 in our multiplication. 1 multiplied by anything is the same thing. If it is multiplied by 10, it is 10, 0 is 0, whatever. So when you multiply 1 by any or to any, there will be no change. So what we do is the most significant bit, we keep it always 1 in our fraction, and in that case, it will not change anything, and we know that it is our most significant bit that is excluded from any calculation. All right, maybe it's still a bit not clear. Let's see how we represent it. Let's say we have this digital number, the way it is. I don't have to know its value in decimal. It is, we are interested in representing it in single precision floating point number. So what do we do? Now we can separate this number, or actually divide it to 1 plus, we put a point here, decimal point here, the rest of the number. So the rest of the number, count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 2 to 12, because the base is 12, now not 10. This is a digital system. In order for you to move the mantissa all the way to the rest of the number, except for the first one here, we said keep it aside, we have to multiply by 2 to power 2 to 12, or 2 to power 12. And in that case, what we did, we transferred, or we converted the number to what? To whole of it mantissa. Okay? So this is mantissa, place it in the fraction part. Okay, we haven't yet done. Now look at this. We assume, let's say we assume that this number is positive, sorry, not negative. We assume. And in that case, the sign number is 0. If it is not said, if it is not mentioned in the question, then assume it positive. Otherwise, we must give you an indication if it is positive or negative, okay? Assume it is positive. So the sign bit is 0. What's left? The exponent. How can I get it? Now we have 12 here. I got this 12. I can convert it to what? I can convert it to simply binary, but it is biased. So I need to add to it 127. Remember the rule? And I said look it up on the internet or from any resource. Why we add 127 for this specific standard, okay? Now, we add 12 plus 127, so that's 139, I'm sorry, not 37, 139. And we can convert this one to binary. Use whatever method you like to convert this one to binary, present it in the exponent. It's positive, so the sign bit is 0, and we have the exponent, whatever it is, after you convert it from decimal to binary, and then you have the fraction the way it is. Forget about this one because we subtracted already, okay, from the whole representation. How do I get it back? How do I get it to its own original form? We have a form to do that. -1 to power of the sign. So the sign here, if it is 0, anything to power 0 is 1. Anything. Anything to power 1 is the same thing. So -1 here represents negative or positive depending on 0 or 1. 0 will take you to positive. 1 will take you to negative. Okay? Now look at the one that we removed. We took from the number. We compensate for it here in the formula plus the fraction. Multiplied by 2 to e minus 127, the bias that we added. Okay? All right. So if you have a number, for example, if you have, this is not the same, okay? This is not the same number here. It has a similar representation, but if we want to get it back to its own representation, what do we have? First of all, we have a negative number. And then we have exponent. The exponent is biased. So what we need to do, we need to find its value in decimal, 145. Now, how do we get it? You can count here, 1, 2, 3, 4, 5, 6, 7, 8. So again, this is 8 as we explained earlier. So this one is 2 to 8, 128. So 2 to 7. So 2 to 6 is 0, 2 to 5 is 0, 2 to 4, 16. So 128 plus 16 plus 1. That's 145 in decimal. Okay, we need to subtract from it 127. Then you get the real exponent. And then this is the mantissa, this is the fraction. The fraction is, we have the decimal point, we have plus 1, so we need to place it again to its own original formula, -1 to 1. Now remember, -1 to 1, the sign bit, multiplied by 1, here we said this one is removed, so 1 plus, remember, 1 plus, so 1 point, the rest of the mantissa, to power what? 145 minus 127, and that's it. If I ask you a question, if you keep it this way, that's enough for me. That's good enough. You don't have to worry about any other thing. Although actually, you just need to count these digits. 18, well, it takes time to count 1, 2, 3, 4, 5. So during the exam or quiz, this one is good enough. That's all I need if I ask. All right. So the exponent actually is 8 bits, or composed of 8 bits. It ranges between -126 to 128. So we can move from negative to positive based on these two, and we can express either too big number, too large number, or too small. Too small means with a lot of decimal points. All right. So we can have a representation of numbers with 129 digits. That's really large representation, although it's a single precision. So imagine the double precision, 32. Not the single, 64, I'm sorry, double precision. That's twice this. The extended one is really high, very high. Usually we do not exactly understand these precisions unless we have an application that actually matter, or where the precision changes a lot of things, even like a decimal point after maybe 20 or 30 digits. Now we have two exceptions. The first exception is when we have a 0. 0 is represented by all zeros here. So if I ask you in the exam or a quiz, represent 0 by a single precision floating point number, you just present all these zeros. You place all of them zeros. That's it. I asked this question before. How about infinity? Infinity, all these ones. This is also an exception. When you place all those ones, then that's infinity. It is known by this way. All right. Let's take another example. Actually, I would leave this example for you to practice. You can just run a conversion between decimal to binary and then represent it by single precision floating point number. You can practice similar to what we explained earlier. Okay. Imagine that we have a single precision, or whatever floating point number, we need to apply some arithmetic operations to this number. How can we solve this issue? So what kind of procedure are we going to have to solve this kind of arithmetic operation? What kind of arithmetic operation? We have addition, we have subtraction, multiplication, and division. And these are the most common operations that we face in our life. But in computer, they are not done straightforward the way we think. They are derived from basic operations that we can make, and we will see them within the coming slides. So we start by addition. Okay, addition in a single precision floating point number for binary system. Now the addition is one of the main arithmetic operations done for all numbers in general and specifically for floating point number, and this addition is extremely critical. Why? Because we use it in other operations, and we will see how. Now when we add two numbers in binary or also in decimal, we call the first one the addend and the second one the ogent. Okay? So when we have these two, the addend and the ogent, we have four main cases. These cases are both addend and the ogent are positive. The outcome is positive. If the addend is positive but larger in magnitude than the ogent, which is negative, then the outcome is positive. If the addend is negative, or the ogent actually, doesn't matter, one of them is negative and larger than the other one, then the outcome is negative. If both of them are negative, then the outcome is negative. Let's take simple examples now. Pay attention to complemented and uncomplemented. Why? Because it matters, it makes difference. These numbers are uncomplemented, so they are in their true form. They are uncomplemented. Now if we add these two numbers, you remember from the last video we explained the first part about adding binary numbers. 1 plus 0 is 1, so 1 plus 0 is also 1. 1 plus 1 is 0 with 1 carried. Let me take the pen so that I highlight things. So here we have 1 carried, and it will keep its value. 1 plus 0 is 1, plus 0 is 1. Then all these zeros, if you add them up, if you sum them up, they will give you zeros. So the result, the outcome is 1, 0, 1, 1. These zeros, if you want to read them, that's fine. 0, 0, 0, 0. Okay, the rest of the number. All right, let's take the second case. The second case, when we have a positive number with the magnitude larger than the negative number. So now look, these are uncomplemented again. I keep highlighting this. Why? Because we will study the complemented numbers and how we can add them. In order for us to do this addition, look at this. This is a negative number. How do I know? The last digit, which is a sign digit, is set to 1, which means this one is negative. So the ogent is negative. Sum up, 1 plus 0, that is 1. So we don't have any carry. 1 plus 1 is 0 with 1 carried. 1 plus 1 is 0 plus 0 with 1 carried. So 1 plus 1 again is 0 plus 1 is 1. We have 1 carried. 1 plus 1 is 0 with 1 carried. Plus 1 is 1. Again, you repeat the process. 1 plus 1 is 0 with 1 carried. 1 plus 1 is 0 with 1 carried, 1 carried, 1 carried. We keep on carrying this 1 until it actually exceeds the 8 bits and it goes beyond that. This is what we call carry. And in this case, we discard it. Discard it, that means we ignore it. It's irrelevant to us. This will be the outcome. Okay? Now this is the case. One of these values is the positive one, which is larger than the negative one. Okay? This is an extremely important case. We discard the sign bit. All right. Now let's take the other case where the value of the negative is larger than the value of the positive. Now let's take this case. 0 plus 0 is 0, 0 plus 0, 0, 0, until we reach here 0 plus 1 is 1. 1 plus 0 is 1. Now again, do the same process. What we are going to get, we will get a negative number. How do I know it's negative? The MSB, actually not MSB, this is the sign bit. MSB for this particular number. Okay? This is the sign bit. So it represents the sign of the number. All right. So in this case, we will end up with a negative result. And this is actually, originally they are in their own uncomplemented form. these two numbers. However, if it is negative, the outcome will be negative, and it is represented by the 2's complement. The computer will understand that it is in the 2's complement. So this is important. Now look at this. The outcome of the positive will remain positive. We will discard the carry, and it remains in the true uncomplemented binary form. This is important. But for the one with the larger negative value, the outcome is negative. And in this case, what kind of a negative value here do we have? We have it in the 2's complement form. We consider it, the computer considers it, not we human beings. Actually, it's done by computer, but we are just trying to simulate what the computer does. So that's exactly the case. We consider it by the 2's complement. -8, how do I know? You can apply the 2's complement weight procedure. So minus 128 plus 64 plus 32 plus 16 plus 8. Check if you get -8 or not. If you don't believe me, try it yourself. Okay. So this is the idea. And let's go to the third case, or this is the fourth, I'm sorry. When we have both numbers in negative, the answer will be, the outcome will be negative, yes. But in which form? Again, in the 2's complement form. Let's apply the procedure. 1 plus 1 is 0 with 1 carried, so we have 1 here. 1 plus 1 is 0 with 1 carried, so we have 1 already here, but we haven't yet done. 1 plus 1 is 0, plus 1 is 1, and we have 1 carried. Apply the same procedure. 1 plus 0 is 1, plus 1 is 0 with 1 carried, again is 0 with 1 carried, 1 with 1 carried, 1 with 1 carried, 1 with 1 carried, until we have a carry totally out of the 8 bits. So what makes to us? We have 8 bits, it's a negative number, I know through this sign bit. How about this one? This one is a discarded carry. It's beyond the width of the whole number, and we discard it. We are left only with this part, which is a negative number represented by the 2's complement. So let's just analyze back again. When one of the numbers is positive and it is larger than the other one, the negative one, we are going to have, likely, we are going to have a carried, a discarded carry. Not in all cases, but mostly we will have a discarded carry. And the same goes to when we have both negatives, mostly we will end up with a discarded carry. This one is already negative, so this one is beyond the width. The width here is 8-bit, count them, 2, 4, 6, 8, whatever beyond this we call it a discarded carry, and sometimes we refer to it by overflow if it is within special cases we will discuss in a while. The overflow, okay, it came directly, I just said about it. Now, assume that we have two numbers to be added. Either they are positive, both of them, or they are negative. So both of these two numbers are either positive or negative. If we get a 1 in the sign bit, now both of them are positive, okay? Now these both numbers are positive. Let's take this example now. Both of them are positive. If we sum up, 1 plus 0, that's 1. 0 plus 1, that's 1. 1 plus 0 is 1. 1 plus 1 is 0 with 1 carried. So 1 plus 1 is 0 with 1 carried, plus 1 is 1. So again, 1 with 1 carried, 0 with 1 carried. So we changed the sign bit. The sign bit, actually we are adding two positive numbers. How the sign bit is changed? This is what we call incorrect sign bit, and it's changed because of the overflow. Overflow is a problem in computing. When we add two numbers larger than the size of the outcome, or what is the permissible outcome. The permissible outcome can fit only 7 digits and 1 for the sign. If we go to the last one, which is dedicated or reserved for the sign, then we have an overflow, and that's the problem in computing, okay? So in this case, we usually have overflow happens if both numbers are positive or both numbers are negative. And it's actually undesired situation or case. Okay, usually it ends up with wrong or erroneous results that we are not interested in. Okay, How about if we add string of numbers? Computers act like us, actually a human being in this case. It's like simulating our character. We add the first two, then we add the third to the sum, then we add the fourth to the etc. So we have a sum of the first two, we add the third number to the sum, then we add the fourth number to the sum of the first three, and you keep on moving. Look at this. We add the first, like this is the first round, we add it, the outcome, we add it to the new number, the outcome, we add it to the new number, and so on. I don't want to do this. I mean, you are already familiar with this summation or addition of binary numbers. Okay, subtraction is totally different. It's a bit new to us. We have two parts. This is what we know. What we know is the subtrahend. This is the part that we are going to subtract, okay? And the part that we are going to subtract from, we call it the manuend. So subtrahend and manuend. Okay, now the idea is like this. How does the computer understand subtraction? We don't have this minus sign in the computer. How about if we convert the subtrahend to negative? How do we do that? How about if we take the 2's complement? Okay, we take the 2's complement, the number becomes negative. If we add it to the manuend, then we solve the problem. So it is done by addition. But before addition, we need to convert the subtrahend to negative, and that's exactly how we do it. All right, let's just take an example. Take the 2's complement of the subtrahend and add the numbers. So we have here the manuend, the subtrahend. So we need to take the 2's complement of this subtrahend. How do we take it? Catch the first one from right side direction. We caught it. Keep it aside. Then take 1's complement of the rest. 1's complement means what? Convert each 1 to 0 and each 0 to 1. So the number will be 1, 1, 1, 1, 1, 1, 0, 1. That's how it will remain. This one, the manuend, don't touch it. Leave it the way it is. Then add them up. So look at this. The manuend, keep it the way it is. Don't touch it. This one, change it the way I said. Hold this one. Convert those, each 1 to 0 and each 0 to 1. That's exactly it. Sum them up. Add. Just normal addition of binary numbers. 0 plus 1, that's 1. 0 plus 0, 0. 0 plus 1 is 1. 1 plus 1 is 0 with 1 carry. Then keep on moving and we will have a discarded carry after all. Why? Because 1 plus 1 is 0 with 1 carried, 1 plus 1 is 0 with 1 carried, so we'll keep carrying 1 until we finish all these possible digits. It will be carried and discarded. That is how we subtract, okay? The manuend. Now, if we take another, let's take this one. Let's take this case. Not B, no, let's take C. Let's take C, okay. Now look, let's look at C. This is the manuend, don't touch it. Come to the subtrahend. For the subtrahend, hold the first one. It's the same here. It happens to be the first one. Hold it, keep it. Convert those, the rest of the number. This one will be 0, 1, 1, 0, 1, 1, 1. Add them. So it is here. Add these two. What will happen? 1 plus 1 is 0 with 1 carried. 1 plus 1 is 0 with 1 carried plus 0 is 0. 1 plus 1 is 0, with 1 carried plus 1 is 1. So here we have already 1 carried. 1 plus 0 is 1, plus 1 is 0 with 1 carried. 1 plus 0 is 1, plus 0 is 1. Then 1 plus 1 is 0 with 1 carried, 1 with 1 carried, 1 with 1 carried, and then we have a discarded carry. Okay. Why discarded? Because we already have filled all the necessary bits that we have. This is extra. It's just going outside. It will be discarded. I hope you guys understood the basic idea. Let's move on. We shouldn't give much of time. Multiplication. Multiplication is done in two different ways, in digital or in logic. We have either the repetitive or repeated summation. Repeated summation means what? Now look at this. Let's assume we have 8 times 3. So we have the multiplicand and the multiplier. The multiplicand is 8 in this case and the multiplier is 3. So we are repeating the summation of 8 3 times. If you sum 8 plus 8 plus 8, it is exactly equal to 8 times 3. We can do that with computer, but it is extremely costly. Costly in what? Now you guys are studying data structures. Means the cost of the repeated summation is high in computer. It takes time. It's not by money in this case. We need time to do this process. So we have a loop of repeated summation and it takes time. Do we have any better choice? Yes, we have a better choice. With shifting and summing, shifting and summing, shifting and summing. How do we do it? Exactly like the multiplication of decimal numbers, the numbers that we use in our daily life. Okay, I explain about those. I explain about this idea. Let's just go to the well, let me explain this example before we go to the shifting and summing. Now look at this. This case, if we think about the multiple summation, now look at this. This is 1, 0, 0. Actually, these zeros represent nothing in this case. They are just zeros. So we have 1, 0, 0. It's actually 4 in decimal. So if we are multiplying this number by 4, then we have to add it 4 times to itself. So we add it to itself 4 times. This is like a repeated summation, which is not really recommended. Let's go to a partial product. Shift and sum, shift and sum. Okay, we apply the same concept of decimal system that we learn in primary school, which means what? We have partial products for each value and its own positional weight. Okay, now look at this. The idea is like this. Look at this. The first one, if we just apply to the decimal, 3, we have to multiply it by this, and it will occupy one side. Based on the 3's positional weight, we start from the same level of 3. Then we move to 2. We move to 2. We give the output, when you multiply it with this, exactly at the positional weight of 2. You start off 1 bit ahead, 1 digit ahead. Okay? And the same goes to 1. This is what we call shift and sum. So we sum these up, but after shifting based on their positional weight. If you cannot understand the idea, don't worry, I'll give you an example. But before this example, now think about this. We have 2 cases in multiplication of binary numbers, same like decimal numbers. If the 2 numbers are positive or negative, the output or the outcome is positive. So if they have the same sign, either positive or negative. If they have different sign, then in that case the outcome or the output or the result is negative. Now for multiplication, I said about the multiplication, now think about this idea. If both numbers have the same sign, then simply the output or the outcome or the result will have positive value. Okay? Now, look at this. If any of the numbers is negative, these are the steps actually. If any of the numbers is negative, then we need to have its true uncomplemented form. Why? We represent negatives by 2's complement in computer, most of the case. So in this case, we need to get it back to its true form. How do I know it is negative? The sign bit. You need to check the sign bit. Once you change it to its true uncomplemented form, then you can create what we call partial products, starting with the least significant to the most significant. And each time you shift based on the positional weight. And then the fourth step, you add these partial products. Now, finally, if the signs are different, you need to set the sign bit. If they are equal, then you need to leave it the way it is. But here is the thing. Numbers in computer system are designed to be a negative in 2's complement is form. So you need to take the 2's complement. If positive, leave it the way it is after summing up the partial products. Not clear? No problem. Let's take an example and you will understand by example. Okay? Now we have these 2 numbers to be multiplied, the multiplicand and the multiplier. Now look at them. Well, this is positive. How about this? This is negative. Well, okay. So one of them is negative, then the outcome is negative. So keep it in mind. The product is negative. Okay? I forgot to tell you, usually the outcome The result of multiplication, we call it the product. So the product in this case is negative. Keep it in mind. All right, let's take the 2's complement of the multiplier. Y is negative. We need to take its true form. How to take its true form? How to reverse this one to its own true form? Well, take its 2's complement, it will get back to its own true form. Why? Because this is 2's complement. It's negative. All right. How do we do it? Hold the first one. This is the first one. This one is the first one. Hold it. Move to the next. Invert each 0 to 1 and each 1 to 0. So it will be 0, 0, 1, 1, 1, 0, 1, 1. This is the number. Okay. Now start the partial products. How do we do it? Partial products start from the least significant. We converted this one, right? So this will be our multiplier. Not this one. This is in the negative form. We need to uncomplement it. Okay? So start. Now if it is 1, the same number will remain, because multiplying 1 to any number will remain the same. Same like this applies to binary and applies to decimal, or applies to any other numeric system. Okay? So 1 times the same number, it will remain the same. If it is 0, it will be 0. But we need to pay attention to the positional weight. When we start with the least significant, we start from this side. Okay? So 1 times 1, 0, 1, 0, 0, 1, 1, it will remain the same. List it down. Go to the second. The second number, multiplied, is also 1. So we start from here, based on the positional weight. List down the number the way it is, because it's 1. Okay, now sum up. So 1 will be dropped down. We consider that it has no addition. Drop down the way it is. 1 plus 1 is 0 with 1 caret. 1 plus 0 is 1. Plus 1 is 0 with 1 caret. 1 plus 0 is 1. Plus 0 is 1. 1 plus 0 is 1. 0 plus 1 is 1. 1 plus 0 is 1. And 1 also will be dropped down. There is no any addition here. You can consider 0. 0 plus 1 is 1. Okay. That's not the end of it. Still we have numbers. 0 multiplied anything here. So we multiply 0 by this one is 0. List them down based on the positional weight here of 0. So all zeros sum up the same number. Just add 1 digit. Why? Because you need this digit after a while. Okay. Just add it. Because we have here no digit. Just add the 0. Then take the next step 1. So list down based on the positional weight. Now go down exactly to the positional weight. Now look, this is here, same number, sum up, and you keep on doing this until you reach the end. It's difficult. Well, it's not difficult. It needs patience, and it needs actually opened eyes and like concentrated brain, so that you don't make a mistake while doing this. We human beings usually make mistakes while doing this addition. Why? It's too long, and you may not see it, or maybe your eyes will just one of these numbers will just run from your eyes. But never mind, the computer doesn't do that. The computer is extremely accurate while doing these. Do I ask these questions on the exam? Not likely. We have better questions to be asked. But yet, maybe in a quiz I would ask such a thing. I wouldn't make it that much long. No. You just waste your time over this question. We have so many other questions to ask. All right, let's move on. Now, do not forget that this number is not the end. Why? Remember that we had one of them negative and the other one is positive, so they had different signs. So we need to add 1 for the sign in front of the MSB, the most significant bit. That is the representation, do not forget it. Now, this is not the number I'm interested in. Why? Now look at this. This is a value. It's not my result. My result is a complemented number. Why? Because it is negative. Do you remember we said this is complemented? We uncomplemented it. We uncomplemented. So before we provide the sign bit, we need to complement, not uncomplement. We need to complement this number. How do we complement it? Hold this one, change each 0 next to it to 1 and each 1 to 0. So 0, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 1. Okay, add 1 in front here for the sign bit, and that's it. You're done. Okay, division. Division is, we can say it a special case of multiplication. How, you will see, and it is composed of the dividend and the divisor. So we have the dividend and the divisor, and the outcome or the result is called the quotient. Okay, how do we do it? Now for the division, actually we can subtract the number of times the dividend, we subtract the divisor a number of times from the dividend. Okay, and in that case, what we need to do is subtracting the dividend multiple times, and whatever, if there is any remainder, then we call it a remainder, and the outcome we call it the quotient. All right, how do we do it? Now look at this. Let's say if we are dividing 21 by 7, then what we need to do? Subtract dividend minus the divisor, first round or first subtraction, then again, until we reach to 0, or if it is not 0, it will be a remainder. All right, so what's the result in this case? How many times we made the subtraction? 1, 2, 3. That's the outcome, the quotient. Is this practical? Of course not. Does the computer do this thing? No, not exactly. We have another way to do it. What we do it is like very similar to the multiplication. We have cases. If the signs are same, then the quotient is positive. If the signs are different, then the quotient is negative. Okay, when the numbers are divided, now both numbers must be in the true and complemented form. If one of them is negative, you need to uncomplement it. So you take the 2's complement of the number to reverse its complementation in this case. Okay? These are the rules. I don't need to read them. I will tell you how we do them in steps. Okay? Let me show you in steps. In steps it will be much easier. Now, first of all, what we need to do is we need to initialize a 0 for the quotient. The quotient will be 0. Totally 0. Now these two numbers, 2, 4, 6, 8. So 8-bit. Now look at these two numbers are positive numbers. So they are positive, they are in their true and complemented form. We don't need to uncomplement anything. They are not complemented. Alright, initially we need to initialize. This is the first step. I said I'm not going to read it, I'll show you in practical. Okay? We need to initialize a quotient. Initialize it by 8 bits. 0, 0, 0, 0, 8 times, 8 bits. Okay? Now, we take the first round. The first round is what? We complement this part and add it to this. Complement this part means what? Taking the 2's complement, adding it to this one means subtracting it from this. Okay? So this will be the subtrahend. Okay? Now look at this. 0, 1, 1, 0, 0, 1, 0, 0. This one, this is the number. Take the 2's complement of this, hold the first one. This is the first one. Then convert or invert or change each 0 to 1 and each 1 to 0. So it will be 1, 1, 1, 0, 0, 1, 1, 1. Sum them up. Add. 0 plus 1 is 1, 0 plus 1 is 1, 1 plus 1 is 0 with 1 carried. 1 plus 0 is 1 plus 0 is 1. 0 plus 0 is 1, 0, sorry, not 1. 0 plus 0 is 0. 1 plus 1 is 0 with 1 carried. 1 plus 1 is 0 plus 1 is 1 with 1 carried. 1 plus 0 is 1 plus 1 is 0 with 1 carried. Okay, now here's the thing. This is what we call the remainder of the first summation. Actually, it is addition, but summation and 2's complement. Since this one is not 0, okay? It's not 0. Now, we have 1 carried. Actually, ignore it, discard it. Whatever carry you get, discard it, okay? So, since this one is not 0, add 1 to the quotient. We initialize the quotient to 0, add 1 to it. Okay, so 0, 0, 0 plus 0, 0, 0, 1, that is all zeros, the least significant bit is 1. This is not the end of it. Let's go to next round. Next round, we do the same. Okay, but we do the same with what? take the remainder and add it to the subtrahend, to the divisor. This one, which is complemented, the complemented divisor. So take the partial remainder, and add it, okay? Add it to what? To my divisor, which is complemented in this case. Do the same process. 1 plus 1 is 0 with 1 carried, 1 with 1 carried, 0 with 1 carried, 0 with 1 carried, and keep on moving, okay? You get the outcome. If you have any carry, ignore it, cancel it. So this one is not 0, add 1 to the quotient. Since this one is not 0, add 1 to the quotient. So we have 0, 0, all zeros plus, 1 plus all zeros 1. What will that do? 1 plus 1. 1 plus 1 in binary is 1, 0. So we'll have all zeros 1, 0. So 0, 0, 0, 0, 0, 1, 0. Okay? Still we are not yet done. The quotient is not 0. Apply the same. Take the quotient, sum it up with the 2's complement of the divisor. Do the same. If you get, again, another positive quotient, by the way, sorry, I wanted to say this thing I forgot earlier. The quotient is not 0, and at the same time is not negative. It's positive. It's also important. It has to be either 0 or negative to stop. Okay? Now, the quotient is positive, add 1. So we have 1, 0. Actually, take this one. You can just write it, ignore reading it. You can just write it. So 1, 0 plus 1, that is 1, 1. So 0, 0, 0, 0, 0, 0, 1, 1. Okay? Now, next to that, what are we going to do? Again, we have a remainder, positive 1. Subtract or add it to the 2's complement of the divisor. That means subtract this number from it. Okay? Do the same process. Let's sum up this one. 1 plus 1 is 0 with 1 carried. 1 plus 0 is, here we have 1. Okay? 1 plus 0 is 1. Plus 1 is 0 with 1 carried. Again, 0 with 1 carried. 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 1 carried here. Discarded, ignored. So we have a 0 remainder. Add 1 to the quotient and you're done. Why? Because this step is concluded, done. We reach to 0 quotient, 0 remainder, not quotient. Okay? Take the remainder. This is 0. Now add 1 to the quotient. We have 1, 1 plus 1, that is 1, 0, 0. So we have 0, 0, 0, 0, 0, 1, 0, 0. Why? This is 3 in decimal, plus 1 is 4. 4 is represented by 1, 0, 0. Double check it. Okay, that's the process. And you are done. And this is the end of this video. I'll upload another video later on. Until then, have a good time. Goodbye.